In this video, I am going to go over the solutions to the midterm review questions. The first page of the PDF is the normal distribution chart with the percentages broken down by the standard deviations. This is known as the 68, 95, 99.7% rule, corresponding with the percents as we move out 1, 2, or 3 standard deviations. This is also known as the empirical rule. So you should have a copy from me. It's also here on the front page of the midterm review for you to refer back to. Our midterm directions have changed since I sent this out to you. So our midterm is now going to be a take-home midterm. It will cover chapters 1 through 4. You are allowed a calculator. You're also going to be allowed access to a computer or any other resources so you can read through your class notes. Of course, you're allowed the yellow distribution sheet because it's part of your notes, and then you're allowed unlimited notes because you'll be working on this at home. I recommend reviewing your group quizzes and graded assignments, as well as looking over this review. And then the exam will probably be more on the side of response questions and multiple choice. And you won't need to use a z-table because you'll have access to StatCrunch. I'm going to give you 1 week to work on the exam. And then you will have the option of printing it out in handwriting or typing on it using Word or a PDF, your choice. And then you're going to submit either pictures of your handwritten exam or your PDF or doc file back to me in Canvas. Let's take a look at the review questions. Keep in mind these are here to help us review concepts. You're not going to see these exact questions on the midterm, but you want to read through and think about the concepts and make sure you're comfortable solving all of these. So the first question compares two groups of male runners. One group is male runners and one group who are non-runners. And then we're told that their heart rates in beats per minute vary from runner to runner according to N 104, 12.5 in parentheses distribution. So this is shorthand. This tells us it's a normal distribution. That's what the N stands for. The first value is the mean, and the second value is the standard deviation. So for runners, they have a mean of 104 beats per minute and a standard deviation of 12.5 beats per minute. Then we have the second group, the non-runners. So after the same amount of exercise, their heartbeats are N 130, 17 distribution, meaning their mean heartbeats per minute is 130 and their standard deviation is 17. So we do see a difference between male runners and non-runners comparing on the treadmill. So we're asked to figure out the middle 68% range for runners and similar for non-runners. So you could sketch out a distribution, as I've done down here at the bottom, and label it with the means at the center and use the standard deviation to add and subtract. So I drew two distributions in part C for runners and non-runners. If you want to do it just by adding and subtracting, we would say, well, we know 68% corresponds with one standard deviation. So for the runner 68% range, I start at 104, and then I'm going to add and subtract 12.5 heartbeats per minute because that corresponds with one standard deviation. I'm using this symbol plus or minus, which tells me I'm going to add to find the upper limit and subtract to find the lower limit. So over here on the right side, what I've done is subtracted 104 minus 12.5 to get 91.5, and then added 104 plus 12.5 to get 116.5 for the upper limit. So that's the range of the middle 68% of heartbeats per minute for runners. Non-runners are similar, 130 plus or minus 17. So we're taking the mean, adding and subtracting one standard deviation. And so we get the lower limit of 113 and the upper limit of 147 for the middle 68% of these runners, non-runners. All right, question B asks us what's the highest heart rate for the top 2.5% of runners? And what's the highest heart rate for the top 2.5% of non-runners? So here we can look back at our distribution sheet and think about the fact that the top 2.5% corresponds with adding two standard deviations. And so for the runners, we take the mean, 104, and we add 2 times 12.5, that's the standard deviation. So that calculation becomes 104 plus 25, or 129 beats per minute. So that is the highest heart rate for it should say lowest for the top 2.5%. So we're trying to figure out where is the top 2.5% start. So maybe I could have phrased this a little bit better, but I think you get the idea. So from 129 beats per minute and up is the top 2.5% of runners. Similarly, for the non-runners, we take 130 and we add 2 times 17 to get 130 plus 34, or 164 beats per minute. So 164 beats per minute and higher are the highest heart rates for the top 2.5% of non-runners. And then here's my sketch of the distribution. If I ask you to sketch a distribution, I'll try to give you the graph and you just have to label it, or you are welcome to sketch it by hand, and I am in no way concerned about your ability to sketch. I just want to see the values labeled down here. So here are our runners, and we started at 104 and then added and subtracted 12.5 for each standard deviation. And then non-runners, we started at 130 and added and subtracted 17. It's important to make sure we label our graph with the units, so both of these are labeled as heartbeats per minute. Question 2 tells us researchers are comparing hospitals in all 50 U.S. states and the District of Columbia. Explain clearly why the researchers must compare rates of hospitals, and here they're using hospitals per 100,000 people instead of counts of hospitals in each state. So we know each state in the District of Columbia has a different population. A state like California has the most people in the country, and so if you just compared numbers in California to numbers in places like District of Columbia, which is much smaller, the counts in California would be much bigger. So in order to do a fair comparison, we want to look at the rate. So we say in order to compare, we must have the same size groups to find the rate of doctors and hospitals for that group size. Comparing hospitals per 100,000 for people allows us to compare the rate and not just the total for each state and the district. Question 3 talks about parking laws. So we're told that until 2002, the thousands of foreign diplomats in New York City could violate parking laws. And so before 2002, the mean number of unpaid parking tickets was 19 and the median was 26. So before 2002, the mean was smaller than the median. So if we think about the shape of that distribution, I did a little sketch here, we see since the mean is less than the median, we expect a left tail distribution. And so my little sketch here shows a distribution with the tail skewed out to the left side. And so that would be interpreted as most diplomats are having lots of tickets and only a few diplomats had very little tickets before 2002, because we've got that tail out to the left, meaning few diplomats had a low number of tickets. Most diplomats had a higher number of tickets. After 2002, the mean, when they started charging, the mean number of unpaid parking tickets was 8 and the median was 3. So that's a shift in the relationship. So after 2002, or since 2003, the mean is higher than the median, and so we expect a right tail distribution. So in my sketch here, I sketched out a little right tail, and I said most diplomats have a few tickets, so there'd be a small amount of diplomats that had a lot of tickets, but most have a few. So you can see the peak down the low side of the graph. Question 4 tells us about a phone survey. So Coca-Cola has hired you to conduct a phone survey about favorite beverages by calling 400 people. Write a letter to a Coca-Cola executive explaining the types of bias and problems you expect in this type of study. In your letter, also explain the best method for determining which numbers you should call. So I said, Dear Coca-Cola executive, a computer should be used to select a simple random sample of phone numbers for 400 people. A random sample will reduce bias. We expect that the survey will be biased towards people with strong opinions about beverages, since this is a voluntary response. I think the scanner cut me off. So you could also, if you wanted to explain stratified random sampling, so you could say, separate people by zip code or area of the country or age group, and then do your random sample. I recommended a computer because having a computer do the sampling, whether you're doing stratified random sampling or simple random sampling, or you could even describe a cluster sample here, a computer is going to randomize and reduce the bias better than we could on our own. Question 5 is a two-way table. So the rows correspond with females and males, and the columns correspond with different activities. This data is from college students in Irvine, California, who were surveyed about their preferred activities when they were not studying or working. So the first thing you have to do is total up the columns and the rows. A two-way table like this is used to store categorical data. So here, one of our variables is the gender, and our other variable is the preferred activity. All right, so you can check your values to make sure your column totals and row totals match mine. Question B asks, what is the probability that a randomly selected student, male or female, so out of everyone, rank going to the gym as their preferred activity? So we would say probability of going to the gym. This is a marginal probability because it's looking at everybody who like going to the gym out of everyone total. That numerator 50 comes from the margin, the column total for going to the gym. We're adding up males and females. And then it's out of all 276 folks surveyed. So you can leave probability answers as fractions, 50 over 276, or you can convert them to decimals, in which case this would be 0.1812. In general, it's a good idea to round to 4 decimal places. Question C says, if we select a female student at random, what is the probability that she prefers video games? So this is now restricting us to just females, so this is a conditional probability. So in probability notation here, I say P for probability, and then in parentheses, I put what I'm counting, the video games. And then I use this line for the restriction. So I say this is restricted to females. So that line tells me my condition. So the second part, the line, which restricts to the females, corresponds to the denominator, which is 139, which is the row total for females. And then I'm just looking at a female row for my calculations. I'm not incorporating any of the numbers from the males. And so we see 18 females like video games. So this calculation is 18 out of 139. You can leave it as a fraction or convert to decimal, which would be 0.1295. Your choice. Question D says, what's the probability that a student is male given that the student prefers sports or dance? So now our given restriction is that the student prefers sports or dance. So this is a conditional probability, and instead of being restricted to a row, now we're restricted to a column. In this case, the column that we're restricted to is sports or dance, and there are 59 folks in that column. So in probability notation, we say probability male, and then we use a line to say given or restricted to sports or dance. So that second part, sports or dance, corresponds with our denominator 59 because there are 59 students in the sports or dance column. And then of those 59, 21 are males. So you can see we just looked right at that sports or dance column to get these numbers, 21 over 59. And then as a decimal, that would be 0.3559. Part E asks, if we select a student at random, what is the probability the student is both female and prefers hanging out with friends? So this is an example of a joint probability. So we're looking at the probability that someone is female and hanging out with friends is their favorite activity. So we come up here to the table and we look inside the table to find how many students are female and like hanging out with friends. So that's 32. And then this is out of everybody surveyed because it said if we select a student at random. So this is going to be 32 out of 276. It's helpful to remember that joint probabilities are out of everybody total. So 32 out of 276 would be 0.1159 as a decimal. Part F asks us, is ranking Netflix or TV as a preferred activity independent from gender? So here's where we have to compare marginal and conditional probabilities. So the marginal probability that someone likes Netflix or TV is 68 out of 276. You can see up in the table. The 68 comes from the column total of Netflix or TV, and the 276 is everybody surveyed. So that's our marginal probability. And 68 out of 276 as a decimal is 0.2464. Now we have to pick one of the conditional probabilities to compare to. So I picked the condition being female. You could have also picked the conditions being male. Either way, we'll see similarities or differences. So we did the probability of Netflix or TV, given that the student is female. So our denominator is 139, just the females in this study. And 24 out of 139 liked Netflix or TV best. And so as a decimal, that is 0.1727. So just inspecting the difference, 0.1727 looks far away from 0.2464, but I want to check to see that they're different mathematically, so you can divide to check the ratio. It does not matter if you choose the larger or the smaller number first. Remember, what we say is close to 1 in a ratio is if we get a value between 0.95 and 1.05. So here when I divided, I did 0.1727 divided by 0.2464, and I got 0.7009. So that is far from 1. So then this is not an independent relationship. There's some sort of association. So my arrow here is noting that this is far from 1, and the relationship is dependent on gender. So what that's saying is it looks like females are less likely to choose Netflix or TV as their preferred activity. If you had done the conditional probability for males, you'd get a higher value, and when you divide, you'd still get something different from 1. Question 6 tells us about adult female heights. They have a normal probability distribution with a mean of 66 inches. That would be 5 feet 6 inches. And a standard deviation of 3 inches. So I asked you to think about what is the probability that a randomly selected female is more than 63 inches tall. So using the 68, 95, 98.7% rule, I sketched out a little distribution here. And I put 66 in the middle, and then I counted down 1 standard deviation to get to 63. And so I can add up the areas there to see, okay, 34% plus 50% is going to add up to 84%. You could do this in StatCrunch as well. So if you want to go into StatCrunch, you would put this in the normal calculator. So let's pause and go into StatCrunch and see how this would work. Okay, here I am in StatCrunch. I'm going to open a blank StatCrunch. And then I'm going to go to Stat, Calculators, and choose a normal calculator. And then I'm going to input our mean and standard deviation. So here the mean height was 66 inches, and the standard deviation is 3 inches. And I want to know the probability someone is greater than 63 inches. So I'm going to shift to the greater than. And I put a 63 in here, and I get compute. And when we did this using the 68, 95, 99.7 rule, we got about 84%. So StatCrunch gives us something really, really close, 0.8413, which you would round to 84.13%. So know that if you're doing this calculation in StatCrunch, you're going to get a more accurate answer, and it'll usually involve a decimal. If you're doing this calculation with our 68, 95, 99.7% rule, you'll get a very close answer, but you're less likely to have a decimal because your values are going to be a little bit rounded. Either way is okay for me. You can write a note if you want to say I did StatCrunch. And if you're typing on your exam, you could take a screenshot of this in StatCrunch and paste that in if you like. If we click on the 68, 95, 99.7 ticks, it draws in what we saw in our distribution with 66 as our center, and then 63 is when we go down 1 standard deviation. Question 7 tells us about scores on the final exam in Professor Meyer's statistics class. So we're told those scores follow a normal distribution with a mean of 82 and a standard deviation of 5. So we are going to use this information to answer the following questions. So the first question tells us Ron scored 88 on the final, and we want to calculate Ron's z-score. So remember, the z-score takes the value and subtracts it from the mean, and then divides it by the standard deviation. So we took Ron's score of 88, subtracted 82 because that's the mean, and then we divide that by 5. So 88 minus 82 is 6, so Ron actually scored above the mean. And then we do 6 divided by 5, we get 1.2. So that's a count of how many standard deviations Ron scored above the mean. And I put a little note here, positive z-scores are above the mean. This is a count of how many standard deviations away from the mean. And then the next question is a multiple choice asking us just to explain, what does this mean about Ron's final exam score? So just what we said, we're going to circle choice B. Ron's final exam is 1.2 standard deviations above the mean. And then Dan also took Professor Meyer's class, and the z-score of his final is negative 2.4. So we have to interpret what this means. So we know Dan is more than 2 standard deviations away from the mean. So we would say his score is actually considered unusually low. So the best answer choice here to describe Dan is that his score is much lower than average. So that our videos aren't too long, I'm going to stop here and then do part 2 to this video so you can watch the video in 2 separate parts.